like countable and countable is like more like a sophistication issue, but not a knowledge issue. So if like you think about, you know what is countable, what is uncountable, maybe you can try some problems here, and you will find out actually you don't know anything. How about we do reviewing first? So the cardinality is about like how we measure a set, how big is the set, like in magnitude. What do I mean by magnitude? Is like when originally we think sets like this one. So you got finite sets, and here is infinite sets. We're thinking about this kind of structure. And this gives you like if A is infinite, and like we say B is finite. So B, subset of A is finite. Then A minus B is infinite. Right? We're thinking about this magnitude of things. Like you pull out finite elements from an infinite set, you get an infinite one. And now you're not thinking about this one as a whole part of infinite set. You're thinking about something like finite, countable, uncountable. So same idea. We're thinking about like uncountable is something like so large and in magnitude it's larger than countable sets. Countable is like the least infinite, lowest infinite. So we're thinking about something like, okay, A is uncountable. A is countable. Then A cross B is uncountable. You should think it in this way, right? So it's about like if we pull out for countable elements from an uncountable set, it's like same effect as we pull out finite elements from a countable set. It's like very large, a little bit large, and very small, something like that. And actually, this one holds. I'm not going to prove this right now. I'll prove it maybe at the third period. We will not test this. But I want you to have this kind of feeling about what is accountable, what is countable, how big it is, by thinking about I'm pulling out something or adding something. So another way to see this is like if A is uncountable and B is countable. And actually, just like when we're thinking about infinite sets and finite sets, if we put infinite set union some finite set, then you still got a set magnitude of equals. This one is the same, right? You're thinking about like encountable is a much bigger thing. Just a feeling. I'll prove it in the third period. All right. Okay, so maybe some preposition about countable. I think you have gone through that preposition 1 about countable sets are the smallest infinite sets. What do you mean by this? Is like A is infinite, then there exists the E prime. A times countable. So talking about countable, we're thinking about counting things. All right. So how to count things in an infinite set? Just pull out one element. After you pull out one element, you pull out the second element, and third and fourth, and go on and so on, and prove that okay, the procedure is never stop. It's not going to. It's not going to stop, and so you get an infinite set. Proof. Big element A1 and an element the procedure goes into A is infinite. Consider the I. It is countable. It's quite straightforward, right? It's just about counting things. And we can think about like, again, we're back to this kind of, right? So a subset of countable set. This proves that a countable is in this part, all right? It's greater than finite, but there's nothing below it because any infinite set has a countable subset, which means that you cannot find a notion of infinite that is smaller than countable. Right? If you can find that kind of infinite set that is smaller than countable set, the subset of it cannot be bigger than or equal to countable. So we're thinking about, again, that graph. We're thinking about, okay, here's finite. Maybe here's countable. And here is, we don't know what it is. But you know that it's infinite. right? This part say that if A is infinite, A in here, then we can find a subset that is bigger than this one. That is impossible, right? It is my subset. It should be smaller than me, smaller or equal than to me, right? So it cannot be here, which means that countable sets are the smallest infinite sets. Let's try question. So again, this the structure. So the subset of countable subsets, countable sets is Apples count another statement is infinite subsets of countable sets is countable. The same. How to prove this? Okay, so again, the countable is about counting. So we're not gonna to give you a rigorous proof, but I'll give you a notion, intuition about how to do this proof. So you're thinking about like A is countable. So you provide a bijection between F, this bijection. So now this one, A1, 1, A2, 2, A3, 3, A4, 4. And you delete out, going for two more terms. A6, 6. And like delete some of the elements here. So we're saying that maybe in B, A equals to, maybe, I'm just saying that equals to A2, A5, something like that, something like this. Then you can get A2, 1, A5, 2. It's just like you're doing this. So you can still count. And the rigorous proof will be like construct a sequence ni such that a and I is equal to a. Right, so it'd be like you're saying that b equals to some a and I. So you put, you're thinking about like some g equals to y. No be a rigorous one, but it's same if you have this kind of thinking.
3, countable union of countable sets is countable. We're thinking about something like A1 equals to A11, A12, A13, A2 equals to A21, A22, A23, A3 equals to A31, A32, A33, and so on, and so on. And you do the counting like this. So you count everything. And try to find a correct counting strategies. Important to know like what set is countable, what set is not.
What is countable union?
Countable union. So it means that let's say is countable. And you're thinking about this one is countable. So you have countable sets in union.
Can you give an example uncountable union?
I can, of course I can. So, example would be examples. Countable union. The first example we'll use later on would be one would be this one, and Z. Or I think a standard example would be something like of course, you can change different slide here, just make it countable. You can have countable. So the notion of like infinite union would be like if I say A in I mean
problems? No. So this example actually gives you something like,
Wait, so both of these are countable units?
because n is countable.
Okay.
We also can like think about like n-countable union, it's just like change it.
we're thinking countable and countable would mean that the index is here. So the finite union means like your index is finite, but not your set is finite.
So if I change n to be like r.
Yeah, it
then-
would work.
then- then-
It will be uncountable union. Proposition 4. Sorry, it's not proposition 4, it should be equivalent, right? This one. Because I think all agree that this one is countable, right? And so this one is countable. Okay. Is that okay? Okay, so proof. This one is countable. Yes, countable. And we know that you can see, one can see U as M in Z, and N equals to 1. This one is an infinite subset of this one. So it's an infinite subset of countable sets. So it's countable. Back to this one. You're thinking about like 1/1 here, 1/2, 2/1, something like 1/1, 1/2, 2/1, 1/3, 2/2. And you just delete this, you do this kind. And you have, this one gives you positive integer. And this one gives you positive irrational. And if it gives you positive rational, you combine with negative rational, both countable. Countable sets, a finite union of countable sets should be countable, just like doing with integers, 1, -1, 2, -2. So you do like 0 and 1, -1, 2, -2, 1/2, -1/2, 3, -3, 1/3, -1/3. Something like that, you can do the cube. It's about counting things. Any questions?
Sorry, what is the MN equals to?
MN, oh, I mean GCD, greatest common divisor, 最大公因数。But R is not uncountable. R is not countable.
usually prove something is not countable by using contradiction. So thinking about like, if it is countable, then what happens? Intuition would be like, if I say it's countable, and I say that there exists a bijection, I'll say that, okay, after you construct a bijection and prove that you miss something, something cannot be mapped. Right. Suppose not and R is bijection. So we're trying to do this 0.81 and 1 point and 1 plus I think, sorry, we should do this first. 0, 1, right? Be easy. 0, 1. 1. Oh, just a symbol thing. I figure out that. Sorry, I found that some of you will use this symbol, right? When you say that set to set, you use this kind of arrow. You say element to element, use this kind of arrow. So there should be here. And to make sure you know how these symbols are used. Ah, my grammar. Projection 0.811, 812, 813, blah 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 blah. 2, 0.821, 822, 823, blah blah. 3, 0.831, 832, blah 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 blah. And that's consider number. Consider number 0.B1, B1, B2, B3, where BI equals to 1 if AII equals to 0 and BI equals to 0 otherwise. So you know that you're thinking about constructing something that's different from here. You're talking about like, I have missed something. So it cannot be this one. The new constructed cannot be this one. So maybe we can change a digit here. Or we change A11. So I'll say that A11 is not equal to B1. So this two numbers not the same. And the same trick goes on the second. So the A22 is not B2. So these two are not the same. A33 is not B3. So these two are not the same. So this one is not any 0.A11, A12, or I1, AI2, AI3. Do you follow me? So you know that 0.B1, B2, blah 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 is not.
Wait, sorry, I can't read the. You're writing it.
Where? Right.
Yeah, so BI is 1
If
equal.
AII equals to 0.
Oh, it's II, okay, I see.
It's not mapped.
So,
So R is
so
not countable.
So, if so we look at the diagonal.
Yeah, we'll look at diagonal, and we change, it's not this one, and change this one, change this one, change this one. So it cannot be, so this number cannot be this number cannot be this number cannot be this, and so on. So I've constructed a new number.
Wait, sorry,
It's clever, but I can't
Well,
do it.
yeah, but sorry, I don't understand what you claim.
I claim that zero.
So if A11 is 0, then you say it's 1.
Yep.
But then if it's not 1, if
it's not 0, I say
say
0.
I see, so it's.
So the A11 is different from B1. A22 is different from B2. So AI is different from BI. Which means that f of I is different from the thing I have constructed. That I have constructed something that is not here. And symmetry goes on when we prove that. Okay, maybe I'll finish this first. So, maybe I'll write it here. I'll write it here. So corollary, R is not countable. Why is this? If R is countable, the subset of R should be countable. But I have found a subset of R is not countable, so R should not be countable. Right? Because countable is the subset of composition. Good. Oh, good.
Hey, I would like to add that maybe this has been mentioned in the video before, but I just forgot. Why can we use this to prove that Q is uncountable?
Q?
Because, yeah, if we
Q?
use the same process, but it leads to.
Oh, because of this number can, this number is not must be rational if you do this to Q. You're thinking about like write Q this way.
Oh.
But this number I've constructed is not Q. It's not may not be in Q.
Yeah, but you have to claim that it won't be in Q, right? Or otherwise we could just prove that Q is.
You can prove.
Okay,
that.
so suppose that number is finite.
Okay, suppose.
Yeah, yeah. Well, the whole point is that the bijection there, all of those go to infinity.
Yeah.
Because if any of those sequences are finite, then up to a very big number, you don't need to keep go on.
Yeah.
But so all of those aij's are infinite long sequences, and so all of those are irrational numbers. And so your B sequence is also infinite.
Yeah.
Because if any of those sequences are finite, then up to a point you don't need that. You don't need that sequence anymore. Or even if they are irrational. No, not, I mean, even if they're finite, then it's all zeros at the end. But but the key thing is that your B sequence cannot be all zeros at the end. Because your so at one of the A sequences or some of the A sequences will have to go on forever because you're covering irrational numbers between 0 and 1. Yeah, and because of that, so your B sequence, well, yeah, so if one of those A sequences is a rational number, then up to a point it will all be zeros.
It may not be like 0.33222.
Or it could be some recurring numbers. That's fine. But the key thing is that, well, to make sure it is a bijection, you need to cover all of the irrational numbers, and so it will go on forever, or at least some of them.
I think in reverse way, so after we prove that Q is countable, so we know that's like.
Okay, that's another way to put it. That's the easy way.
But yeah, I'm thinking more carefully about this. So another very important definition here is metric space, right? So if we see metrics somehow of distance, we're constructing a distance over a set. So we're saying what is the distance? The distance should greater or equals to 0, and we're talking about if the point itself has 0 distance to itself. If it takes 10 point, they should have positive distance. Distance do reflexively, so the distance from x to y is distance from y to x, and you have the trigonometric inequality. So examples, the most common example should be this one. One is trivial. You cannot do this on your test, right? Just put on like 2 sentences, it's alright, but. And the second is trivial. Okay, I'll try to do this. Okay, xi minus yi squared equals to yi minus xi squared. Just write this sentence. If I put this problem on your quiz, just put on this sentence, then you'll get points. I think it's a big hint. Okay, the third one. How do I prove that one? So we're saying that x1 minus y1 squared plus x2 minus y2 x1 x2 minus y2 squared plus y1 minus z1 squared plus y2 minus z2 squared. It should be less or equal to x1 minus z1 squared plus x2 minus z2 squared. Right. time. I think the clock. Oh, I have 3 more minutes, I think. Yeah, I can finish this one. Square. So I want to show this. Or I just broke out every single chalk I use. So this square them out, and you give us like x1 minus y1 square plus x2 minus y2 square. Plus,
Greater or equal.
oh, sorry, greater or equal to, yes, you're right. Check. Correct. Plus y1 minus c1 square plus y2 minus c2 square. And plus 2 x1, oh, right, so I'll put it this way. Sum over xi minus yi squared. Times sum over y minus ci squared. As I'm not so sure if I do this right. Boundary equal to x1 minus c1 square plus x2 minus c2 square.
Yeah, it's confusing because usually x, y is the 2 dimensions of the, yeah, of the R2 space. But now you're using x as, x, y as different.
Yeah, I found that one. So I found it confusing. My homework. Okay. Check if I'm wrong. No, I think I'm wrong. Okay, so just take these things. Gives you 2 2x1 y1 plus 2x2 y2 plus 2 y1 z1 plus 2 y2 z2 plus 2 y1 square plus 2 y2 square is 1 and plus 2 this thing equals to larger equals to 2 x1 z1 plus 2 x2 z2. So
Cauchy.
Yeah, I know, just doing this one and Cauchy.
You can do Cauchy in the roots, square
I
roots.
can do Cauchy in square root. Sorry, that's my fault. I just cannot remember how I do this.
At least we know it's not gonna be in the test.
So,
That would be in the test, sorry. So, it's just keep going on. Sorry, my fault.
applying Cauchy, this will larger or equal to some xi minus yi minus ci. Square, normal square. Yes. Oh, you need to add a absolute value because it is positive. So this is larger than this term. So this will equal to some I minus yi plus some yi minus yi squared. So this one will larger or equal to xi minus y. You use zi. Yes. Yes, just using a Cauchy in the square because this is the sum of the square. This is the sum of square. So you may think that it can apply Cauchy first. So you use it and find it. Yeah, that's the way.
I think we're right. I think we're right. Sorry, that's my fault.
It's alright.
Remember this one, I'll test this.
I will explain more how to using that this will.
I'll put that on the blackboard. You can remember it like in 10 minutes.